Welcome back. In this video, we're going to graph polar equations using our graphing utility. Our objectives here are to graph Rose curves using cosine. We'll graph Rose curves using sine. We'll graph Limacons, and we'll graph Lemniscates. Some items you may want will be your graphing utility. We're going to use the TI-84, and of course your unit circle. Our first objective is to sketch the graph of r equals 2 cosine of 3 theta. A little bit different than what we've done before with the 3 theta here. Because this is cosine, we know our symmetry is going to be respect to the polar axis, and our zeros of r are going to occur at pi over 2, 3 pi over 2, and 5 pi over 2 when we have 3 theta, or at theta of pi over 6, pi over 2, and 5 pi over 6. So let's talk about that for a minute. Keep in mind now we're graphing r equals 2 cosine of 3 theta. So this 3 theta messes with us a little bit. So when we put theta in, here we have a theta of pi over 12. Our 3 theta for pi over 12 is, as I say here, is 3 pi over 12, or pi over 4. When we put pi over 6 for theta, our 3 theta is pi over 2. When we put pi over 4 in, our 3 theta is 3 pi over 4. We're still going to plot points, and we're going to begin with values like 0 and pi over 6, pi over 4, and pi over 3. But the multiplier of 3 on theta moves us to a new location on the unit circle, subsequently changing the value that we're used to getting. That's why theta of pi over 12 moves to 3 pi over 12, or pi over 4. And then we grab the value of square root of 2 over 2 from our unit circle. And then that's how that's simplified. We had 2 cosine of 3 theta, so 2 times the square root of 2 over 2 simplifies to square root of 2. Subsequently, pi over 3 then becomes 3 pi over 3, which is at pi, and the cosine of pi is -1, and 2 times -1 is -2. So that's why pi over 3, well, we really evaluated it at pi. So remember to distinguish between your location on the unit circle and the value, or the ordered pair, at that location. First, we grab a theta, we multiply it by 3, we move to that location, and then we grab the value of the cosine, in this case, at that location. So in order to graph this Rose curve, if you will, we're going to plot the points using the specified symmetry and zeros, and we obtain the following graph. And this graph is called a Rose curve, and each loop of the graph is called a petal. Note that the entire curve is generated as theta increases from 0 to pi. And keep in mind here also that we're graphing this on the polar plane. Our thetas, our angles, are moving along the polar plane here, and this is not the coordinate plane. So our start here with our function r equals 2 cosine of 3 theta. When we put 0 in for theta, the cosine is 1, but 2 times 1 is 2. So our start here is out at 2. And as we rotate around, as our angles change, our values move. So when theta goes from 0 to pi over 3, or pi over 3, our values move down to here. These become the r values. And as we continue to rotate theta around, our r values move and create the petals. Okay, here we're at pi over 2, and we end up with a r value, I bet, of 0, which we had here. And we continue to move through values of theta, plotting those points and we create the third petal, and we come around, and as we get back to pi, we end up, as we head towards pi, and then we end up back at 2 again. So by plotting all those points and moving through theta between 0 and pi, we end up with a rose curve with 3 petals. Some things to note: the curve begins on the polar x-axis at 2 times 1 equals 2, because the cosine of 0 is 1 and we're multiplying by 2. The petal has the length that's the same as the coefficient of 2 on our cosine. So our petal length is this 2 here. And our rose has 3 petals, and we had 3 theta, and also 3 is odd. So a couple things to keep in mind. In our second sample, here was our first sample where we did 2 cosine of 3 theta, where our A was equal to 2, our N was 3, we ended up with 3 petals. Well, if we see down here in our note, when we have 2 N petals when N is even. So this particular diagram has 8 petals, so our N must be 4. This is the graph of 2 cosine of 4 theta. So let's do some graphing with our graphing utility. You want to make sure that your calculator is in polar mode. You can simply go to mode and then polar, and make sure the calculator is in radian mode as well. So while you're in mode, change that to radians, or make sure it's in radians. Now you can set your window to standard. I'm going to view between -5 and 5 on both the x and y axis, although I think in this one I am actually changed my y-axis to -4 to +4. And we're going to play a little bit with this. So let's go ahead and get our calculator set up. So here I have my graphing utility. I want to change the mode. I want to get this into radian mode. It's currently in degree mode. And I want to make sure I can have this in polar. So next to the second button, I've got my mode button. I can go to mode. I'm going to cursor down. I'm going to select radians. I'll hit enter. And I can put this into polar mode right away here. Just below radians, you see function, parametric, polar. So I'm going to put that into polar, and I will quit out of that. And my window, I've already set my window. It looks like my theta is essentially between 0 and 6.28. That looks like 2 pi. My x min and max, because of the size of the things we're going to graph, I'm just going to do -5 and 5 on my x-axis and -4 and 4 on my y-axis. I'm going to do a scale of 1. And we're going to graph a whole bunch of things here. I've already input some of the things we're going to graph. Looks like we're also going to graph 4 cosine of 2 theta. So I'll put that in for you. 4 cosine of 2. And then the theta key is just right next to the alpha key. It's what we normally used as our x when we were graphing on the coordinate plane. So go ahead and put that in. And I don't want to graph those right away, so I'm going to deselect those. So let's go ahead and just graph our, to begin with, 2 cosine of 3 theta. And sure enough, we didn't see where that started, but that started out here at 2 and then followed that path. You might better see that on your calculator. Now let's go ahead and graph 2 cosine of 3 theta and 2 cosine of 4 theta. And we'll graph those simultaneously. So one will be blue and one will be red. And let's take a look at the difference in the petals there. So the red one, there are 8 petals, where our blue one still has its 3. So we had 2n petals, and our lengths are the same. The petals are the same size, that length of 2. Let's look at 2 cosine of 3 theta and 2 cosine of 5 theta now. We'll graph those, so we're going to have a blue and a black. And those are both odd. And the black one has 5 petals, the blue one has 3 petals. And just like the information above, when n is odd, that's the number of petals we're going to get. And they both, again, have a length of 2. Now let's look at, looks like 7 theta. We can hypothesize that that one is going to have 7 petals. And sure enough, that one does indeed have 7 petals. Now let's look at 2 cosine of 3 theta and 4 cosine of 2 theta. So now we have an even value of n, so we're going to have double the petals, but 4, it looks like it's going to extend. We're going to have a longer petal on there. Instead of 2, it's going to be 4. We graph that, and sure enough, we have 4 petals and a length of 4. Spectacular graph there. And that also should have started out here at a value, an R value of 4. Again, because the cosine is 1, but times 4, and we get a value of 4 there. And finally, let's graph 4 cosine of 2 theta and 4 cosine of 4 theta. 4 theta should have 8 petals on it, and they both should have a length of 4. And sure enough, those are our 2 graphs. So again, note the length of our petals is A. In our case, it was 2, and we changed it to 4 for a couple of those. And this would also change our start location, because we were graphing cosine, and we're moving out a little bit further there. When n is odd, the number of petals was exactly the number of petals in our graph, and when n was even, we had 2n petals in our graph. Now let's take a look at Objective 3 and explore limacons. As you can see here, there's a variety of limacons, and it depends on what happens in our equation. So our equations for limacons, you can see here, are A plus or minus B cosine of theta, or R equals A plus or minus B sine of theta. So again, cosine is going to be x and sine is going to be y. So think about how that might open on the x-axis and how that might open on sine might open on the y-axis. Our diagram here shows, what our limacons will look like based on certain conditions, and A over B, the A value divided by the B value, does determine what that looks like. So if A divided by B is less than 1, we'll have a limacon with an inner loop. If A and B are equal, we'll have a cardioid. If A over B is between 1 and 2, we'll have a dimpled limacon. And if A over B is greater than 2, we'll have this convex limacon. So let's make some inferences from what we've already learned about graphing polar curves and how they might relate to limacons. So again, I've written our equations here for the limacons, the cosine version and the sine version. So what we know about symmetry, the cosine version will be symmetrical about the polar or the x-axis, and the sine version will be symmetrical about the pi over 2 line or the y-axis. B, the coefficient on cosine or sine, is going to be a multiplier. That's going to impact the radius or the size or the magnitude, like how big our shape is or how small our shape is. And then it'll also impact how far out on the polar for cosine or the pi over 2 for sine line this curve will extend, just what I'm talking about, how far that's going to extend on our polar axis or how far it's going to come up. Or if it's negative, how far it goes down or how far it moves to the left. And then the A value, that's going to impact our start. It's kind of like a vertical or horizontal shift depending on if we're working with sine or cosine. And then the positive versus the negative, the plus or minus. Positive, the shape's going to open downward. Positive, the shape will open towards the positive polar or positive pi over 2 line, and negative, the shape will open towards the negative polar or the negative pi over 2 line. So just think positive or negative direction like we have done in class. So we're going to take a look at graphing a couple of these simultaneously. We'll look at 1 plus 2 sine of theta and 1 minus 2 sine of theta and see what those look like. Well, what do we know already about this? Since our A divided by B is less than 1, A over B is 1/2, so it's less than 1, this is going to be a limacon with an inner loop. The fact that we're graphing the sine curve means that this is going to open, if you will, on the pi over 2 line. The positive one will open up in the positive direction, and the negative one will open down. Our multiplier here is 2. So whatever our theta value is, whatever the value at that location is, we're going to be doubling that. Think of magnitude or a size of 2, and then plus the 1, we'll have a magnitude of 3. And our start for both of these are going to be at 1 on the polar axis, because the sign of 0 is 0, and then 0 plus 1 gives us 1. So we're going to start at 1 on the polar axis for both of these. And you can see from our diagram here, entered this into my calculator, and we should get the positive sign. 1 plus 2 sine of theta is going to be the blue one. It's going to open up on the positive, and 1 minus 2 sine of theta is going to open down in the negative direction. So here's my calculator. I've input everything in. I've got my window set. Looks like my x and y axes are going to be between 5 and negative 5. And I hit graph, and sure enough, I get that nice graph. So now that we've graphed those, let's take a look at sample 5, and we'll graph the cosine version of these. And here we're going to graph a couple of cardioids. So let's go ahead and graph these two equations with our graphing calculator simultaneously. So I've input everything, 2 plus 2 cosine theta and 3 minus 3 cosine of theta. And let's think about what kind of a hypothesis we can make about this. Since a over b is equal to 1, looking at our notes, we can see this is going to be a cardioid. Cosine means that it will open, if you will, on the polar or axis. The positive one should open to the positive side or to the right, and the negative one, the one with 3 minus 3 cosine, should open to the if you will, to the left. So I'm not sure why I have right and left in quotes. It should be open, should be in quotes. The 2 plus 2 cosine of theta should start at 2 times 1 plus 2, because the cosine of 0 is 1. This is the cosine of 0. Equals 1. That should start at 4. The length of this will also be 4, because the cosine of any value, we won't get any higher than 1, so 2 plus 2 is 4. And then for 3 minus cosine of theta, that's going to start at 0. The cosine of 0 is 1. Negative 3 times 1 plus 3 is 0. Okay, so I have, because cosine of 0 equals 0, make sure you correct that. That's cosine of 0 is 1. And then the length will be 6. So this one's going to be quite large. And we'll see if that even fits on our screen. So going back to my calculator, I'll go ahead and graph those. And I get my two different cardioids. And you can see the blue one did open to the right, and the red one did open to the left, and in fact my window wasn't even big enough with 6 units to accept that whole thing. So in your notes we can see what those two graphs look like. Moving on to objective 4, we're not going to spend too much time on this particular one. We're going to look at circles and lemniscates. Our circles, we've seen enough circles before with our A as our diameter, and half of that would be our radius. And our lemniscates, the sine version here is reflected, looks like it's across the pole, interestingly enough, where our cosine one is across the polar axis. So we've seen some of those same concept before, with the length of the petal being our A value, or the square root of A squared. So our concepts of symmetry and start and magnitude will still apply in these. And then make sure to input equations of lemniscates in your graphing utility. You'll have to take the square root of both sides, because this has r squared and we want that to be r. And we'll get some more practice with this when I see you in class.